Hello all, welcome to the video for section 3.2, properties of determinants. Make that E look a little better. Boom, properties of determinants. So let's open with a little theorem here. Let A be a square matrix. If a multiple of one of its rows is added to another row to produce a matrix B, then we actually haven't changed the determinant at all. So if we perform this elementary row operation, adding one row to another, it doesn't change the determinant. Boom. B, if two rows of A are interchanged to produce, I should really say to produce B, produce a new matrix B, then what happens? Well, it isn't the same any longer, but you just pick up a negative sign. Boom. And then our third elementary row operation, if one row of A is multiplied by a scalar real number K to produce a matrix B, then the determinant of B is just K times the determinant of A. Okay, so now we know how our elementary row operations affect the determinant. This makes computing determinants much easier, actually. Let's do an example here. Here we've got A, a matrix, and we're going to compute its determinant. So the determinant of A. And we use these vertical bars for determinant again, just for ease of writing. 1, 2, 0, negative 3, 4, 5. First thing we can do, and we can really say equals here, not equivalent, because we aren't talking about the matrix, we're talking about this number, talking about the number that is the determinant. And so if we swap two rows, we'll swap row one and row 2. So we can pick up a negative sign here then equals negative. So now we'll do 1, 2, 0, 2, 1, negative 1, negative 3, 4, 5. So here we interchanged row 1 and row 2. Now we can do the things we usually do. Let's subtract, let's clear. The idea now is to row reduce this matrix into echelon form. And then previously we saw that if our matrix is diagonal, then its determinant is just the product of the diagonal entries. So that's where we're headed. This putting our matrix A in echelon form. Each time changing the determinant according to this theorem. Right? This theorem allows us to do any kind of elementary row operation, and we know how that affects the determinant. So now let's do sort of the obvious thing. Let's clear off the 2 and the negative 3 below the 1 in row 1, column 1. So we're going to do row 2 minus 2, row 1. We're going to do row 3, row 3 plus 3, row 1. And according to this theorem, since we're adding one row or multiple of one row to another, we don't touch the determinant. The determinant is unchanged by this action. And so we get what? Our first row hasn't changed. 1, 2, 0. 2 minus 2 is 0. 1 minus 4 is negative 3. Negative 1 minus 0 is negative 1. Negative 3 plus 3 is 0. 4 plus 6 is 10. 5 plus 0 is 5. Boom. And we still aren't quite echelon yet, but we can do, what action do we want next? We want row 3 plus 10/3, row 2. Yeah, that'll do it. And so we forgot a negative sign. Boom, negative sign. Boom, negative sign. We're gonna carry that the whole way through. Okay. So then finally we get our first row unchanged, our second row unchanged, and our third row really not so bad at the end. Okay, and so now this whole thing is equal to negative 1 times the product of the diagonal entries, which is equal to 5. Okay, so significantly easier than using the definition to expand and doing what? This times the determinant of that, plus or minus this times that determinant, plus this times that determinant. and easier still with a 4x4 matrix. Okay, we can sort of use this example and get a quick little result about determinants. Yeah, so let's say, so in general, if A is an n by n matrix and B is an echelon form of A, and I'll found by using, so row replacement and row interchange only, no scaling. So if we eliminate, if we don't do any scaling at all, which is always possible, we don't do any scaling, then something nice sort of happens, right? We've got our regular matrix has been reduced to echelon form, and since B is echelon, it's triangular. Either there's a pivot on each diagonal entry, or it could be 0 too. But certainly it doesn't there's only zeros in this lower triangle. Yeah, since the determinant of B is just the product of the diagonal entries, and since we haven't scaled it all, our only option is we pick up exactly the same as the determinant of this B, plus or yeah, with this -1, which with a -1 for each time we use the row interchange. And so we end up getting that the determinant of A in this situation is -1 to the R times the product of the B pivots when A is invertible and 0 otherwise. And here R is just I didn't write that down. R is the number of row interchanges. That in a little bubble so that doesn't get lost. Oh, all right. And again, this required us to not scale any rows. It would be an easy mistake to forget that. And this quick little observation about how to more easily compute the determinant allows us to prove this nice theorem, which says if A is a square matrix, a square matrix A is invertible if and only if its determinant is non-zero. So now we can go back to our inverse matrix theorem and add a whole other statements to that theorem. Yeah, so in particular, we know that that A is invertible if and only if its columns are linearly independent, and we also know A is invertible if and only if its columns span Rn. So now, since invertibility and determinant being non-zero are equivalent, we get that the determinant being non-zero is also equivalent to both of these. So this determinant is controlling an awful lot about the matrix A. Right? We had that long list of things that are equivalent to being invertible. Now these are all equivalent to computing this single number, which is great. All those things now come down to some number we can compute by hand if we have to. Okay, let's talk about more properties of the determinant. This theorem 3.5 says for a square matrix A, we have the determinant of A is equal to the determinant of A transpose. And the proof idea here is basically, where did I write that down? Oh, yeah. Row expansion across A is the same as column expansion across A transpose. And that isn't a proof, that's just my quick sketch. There's a proper proof in the textbook. This is just the idea is that row expansion across A is the same as column expansion. With an S or with a T? Expansion has to be with an S. No, I'm not sure. Okay. Okay. Oh, right. And the reason we keep on saying for square matrices, I'll give you a second to think about that while I stall and say more words here. The reason that we're always talking in this chapter about square matrices is because we don't have a notion of determinant for non-square matrices. Okay. Okay, one more property of determinants. If A and B are square matrices, then the determinant of the product is the product of the determinants. So the determinant respects matrix multiplication. And this will, yeah, there's a great proof in the book. We won't go through it right now. I encourage you, if you're curious, to take a look. But let's at least verify this for one situation, and we'll talk about what happens with addition in a second. Because you might be saying, well, what about addition, David? So let's compute the determinant of A, the determinant of B, the determinant of the product, and show that sure enough, in this case, the determinant of the product is equal to the product of the determinants. So, Yeah, we know what the determinant of A is. Or let's compute the product of AB first. 1, 2, 3, 4 times 5, 1, -1. Okay. So our arrows are like this. So it's 5 minus 2 is 3. 1 plus 2 is 3. 15 minus 4 is 11. And then finally, 3 plus 4 is 7. And so the determinant of AB is just 3 times 7 minus 3 times, minus 3 times 11, which is what? 33 minus 21 is 12, so the opposite would be -12. The determinant of A is 1 times 4 minus 2 times 3, that's -2. The determinant of B is 5 times 1 minus 1 times -1, that's 6. And so sure enough, yeah, the determinant of the product minus 12 is equal to the determinant of A times the determinant of B. Okay, again, not a proof, just an example. The proof is, yeah, very interesting, but also contained very well in the textbook. So yeah, natural question, once we've seen that the determinant respects multiplication, is to ask, okay, well, yeah, is it true that the determinant of A plus B is equal to the determinant of A plus the determinant of B? The answer is nope. Absolutely not. Almost never. You'd have to work hard. Well, you have to work a little bit at least to find a situation where it's true. So let's, again, I'm not going to prove that, but we'll find an example where certainly the determinant of the sum is not equal to the sum of the determinants. So let's do the laziest possible thing, which is to reuse our computations of the determinant of A and B. We'll take A plus B and take its determinant and show you that it isn't equal to 4. So let's check that the determinant of A plus B is not equal to the determinant of A plus the determinant of B. I'm in the example above. Okay. So A plus B is 1, 2, 3, 4 plus 5, 1, -1, 1. So this is 6, 3, 2, 5. So its determinant is just 6 times 5 minus 3 times 2, which is 30 minus 6 is 24. But this is not equal to, yeah, not equal to 4, which is equal to 6 minus 2, which is the determinant of A plus the determinant of B. Get that backwards? Yeah, minus 2 plus 6. Okay, 4 isn't equal to 24. And so the determinant of A plus B is not equal to, yeah, so the sum is, this determinant of the sum is not equal to the sum of the determinants. And I encourage you to find any other example and check and see. And unless one of your matrices is the zero matrix, I think this is not going to be, yeah, that this inequality is still true. Okay, I'll see you next time with section 3.3. Take care, everybody.